I want to welcome you back from the winter break and also to welcome you to Psych 521 Research Design and Inference 2. Now, we covered a fairly large amount of information last semester, starting with basic descriptive statistics and going through most of the advanced univariate statistics. And again, univariate referring to the DV, how many DVs we're looking at. And that was primarily the theme, that we were looking at inferential statistics, so statistics that were intended to make an inference from our sample to our population. We were looking at parametric statistics, statistics that the outcome is a continuous variable, either interval or ratio data. So basically the numbers have meaning and there's approximately equal distance. The only difference being between interval and ratio of whether that is an absolute difference of starting at zero ratio or more of a hypothetical kind of construct situation like a Likert-like scale. And again, it was almost all exclusively univariate designs, where the DV, the outcome, was always a single ratio or continuous variable. This semester, we're going to be looking at some additional types of statistical techniques. We're going to be looking at multivariate design, so multiple DVs. So a situation where you are trying to predict an outcome, but not just one outcome, multiple outcomes. So instead of just having multiple predictors, we're going to have potentially multiple predictors and multiple outcomes. And as you might quickly imagine, it's simply just yet another level of complexity. It's not necessarily that we're going to be doing anything differently than what we've done in the past. We're simply adding more layers to that kind of statistical onion. We're also going to look at some statistical designs that do not necessarily focus on a DV or an outcome, so more exploratory analysis in large data sets. We're going to talk a little bit about various ways to look at very complex designs. And finally, we're also going to at least touch on non-parametric statistics. Those are statistics where the outcome is categorical. Now, to begin that journey, if you will, we're going to be doing, at least for the first couple weeks, a review of everything that we've covered prior to this semester. So basically, it's going to be kind of a 2-week review of 520. And even as we move into week 3 and 4, we're going to be looking at statistical techniques that we've already dealt with, but we're going to look at them with a little more complexity. We're going to add some more layers. So we want to make sure that base that we're building off of is solid before we start getting into more advanced designs. So today's lecture is really going to be focused on a broad overview of the theoretical concepts of statistical analysis. So we're not even going to be talking about specific statistical analysis, just kind of that base foundation for any research design or any statistical inferences. So again, we start very theoretical, and that's with Mills' canons, the logic of causal inference. And just as a reminder, that in order for us as a scientist to be doing a study where we're looking at data and using statistical analysis, if we are going to make a claim of causation, that we actually found a causal relationship between our independent variables, our interventions, and our dependent variables, our outcomes, we have to establish all three of these through both methodology, logic, and statistics. And the first one is statistics. The variables must covary, and it must be a reliable relationship. So that's what we rely upon as far as p-values, effect sizes, and that we're using the appropriate statistical technique for the type of data we have. But that's just step 1 of 3. Step 2 is the cause must precede the effect. And this is the methodological component. We have to make sure that we've set up our study to where there is no other logical conclusion that the cause was the only thing that changed and that the cause happened before the effect. If we have both of these, we still are not necessarily at causation. We may still be at a quasi-experimental design. The third one is that now this is the logical argument, or if we might call it the actual based on past literature and based on everything that we can make as far as logical arguments, that our methodology had to rule out all other alternate explanations. Now, Mills' canons are a fact. They are not theory. They are pretty much what we have to do if we want to talk causation. But there is a bit of a trade-off in this, that you can see that to do a true experiment that 100% guarantees that you have all three of these components tends to be a very controlled situation. It tends to be a very obvious laboratory experiment. And a lot of times when we're interested in looking at psychological phenomena, this may be an issue because there is no question our participants are going to be aware that they are in a study. So let's move on and take a look at some of the other things we want to consider when we're looking at statistical analysis. So again, another way to look at Mills canons is there has to be a statistical relationship, there has to be temporal precedence, and we have to rule out any confounds. Now remember that if we're talking about inferential statistics, which is our focus, what we're inferring to is population or mu. And it is going to be a very rare, if not a non-existent experiment that truly measures a population. But it can happen. You have to define what your population is. Now, a lot of the times in psychology, especially for broad theories, the population are humans in general, all of us. But especially in applied settings, the populations may be a much more limited scope of who you're actually trying to infer to. However, in most cases, we're not going to have access to a complete population, or the research questions that we ask are going to be broad enough that the population will be hard to sample completely or study completely, which is why we draw a sample. And again, how that sample comes about will determine to some degree. It's one of the first questions that need to be asked when you read a study. If the sample was determined through random selection, in other words, you truly identified everyone in the population and randomly selected them to be in the study, and all of them accepted to be in your study, you've got a stronger theoretical argument for inference. You can infer that that sample is representational of the population. Now, in reality, this rarely occurs. Generally, our sample is going to be a convenient sample or a partial random selection sample. In other words, some people may not be contacted, some people may not be identified, or some people may just refuse to be in the study. That means we no longer have true random selection, but at least we tried. So we want to think about, as far as our methodology, how are we getting the sample? Because it does matter, especially if we're trying to infer to that population. Now, once we have our sample, we're going to do our experiment. We're going to have, for example, 50 people with an effect. So we know this information. We have this information. We have the data. We've got the score of each one of those 50 people. We have done some form of manipulation where we have a group 1 and a group 2. And we've found a statistical difference between those two groups. Group 1 is much lower in their scores than group 2. And that difference in those means is our effect size. That is known. So we now have that information. That's where our statistics come from. That's where our critical values, our p-values, everything that we're calculating, including effect size, is going to come from that actually known data. The inference part is that we're now going to infer to that difference that we found, what would be the statistical likelihood of that difference occurring if we did the same experiment with everyone in the population with the N of our study over and over and over again. So in this particular example, the N of our study was 50 people. So what we're asking when we infer is, what is the estimate of all possible N's of 50 drawn from that population without or with an effect? In other words, how likely is it that we would find this effect due to just pure chance and not our manipulation? If that chance is less than 5%, that's a p-value of less than 0.05. So not only do we have our statistics and our effect size and our means, we have now made an inference that it is highly unlikely that we would have found this difference in a random sample from our population. Now, this is not known. We do not have our entire population studied over and over and over again at the inside of our sample. This is an estimate based on what we know about normal distributions of scores. So mathematically, what we're looking at is we're actually calculating a test statistic out of our sample, whether it's a t, whether it's an f, whether it's a chi-square, whatever the statistic is that we're using, we're actually calculating a test statistic. And from that test statistic, we're basically measuring how large was the effect size. And we often will also get our effect size from this test statistic. Once we have the test statistic, based on our sample, we're going to look at a probability table based on that sample size with the probability of error to find out what would be the minimum score that we would have to find in our test statistic for that difference to be greater than basically a 5% chance that it's wrong. So less than 5% chance it's wrong. 95% chance that we would not find that due to chance. And that's our critical value. Now, as long as our test statistic is greater than our critical value, we've attained that p of 0.05. that test statistic is less likely to occur in the population due to chance. In fact, its chance of occurring due to just pure random chance of the population is less than 5%. And again, where we get this, if we're not using a computer, is from distribution critical value tables. And the way we use these tables is we find the p-value that we want, we find the degrees of freedom that we were actually using, and sometimes these charts might just list n, but we're always using the degree of freedom based on the population size, and then we cross-reference to find the critical value. So in this case, if we're wanting to find a alpha of 0.05 or less, we have a degrees of freedom of the study that we ran of 15, we would need a critical value of greater than 1.753. So again, when we're talking about statistical significance, it's fairly important to recognize the terminology we're using. Test statistic refers to the actual value derived from our statistical test. This is the math that we are doing by hand or letting a computer do for us. This is the value that's attached to the test statistic. And again, the test statistic will change depending on the test. R for correlation, often R or beta for regression, T for t-tests, chi-square is actually a chi-squared. We're usually looking at F if we're talking about ANOVA, and we're going to be talking about some other test statistics notation. But whatever that calculated value is from our sample is the test statistic. The critical value is the criteria for stating that test statistic has a p-value of less than 0.05. So it's based on those probability tables. The p-value is the actual statistical significance value of a particular test. So for example, if I find that my critical value is high enough that I actually have met the requirement, the critical value for a p of 0.01, I could report p of 0.01. If I found my critical value, my test statistic exceeded my critical value so much that it actually was passing the bar for a p-value of 0.001, I could report 0.001. That would be the p-value of the actual test. Now, most computer programs will actually give us the precise p, and again, that's what we'd report. Alpha level is what we've set as far as the criteria of what p-value we'll accept. And again, in the psychological sciences, this is pretty much kind of a gold standard of 0.05 or less. Now, do remember that there is an issue that because of this process and the fact that we are looking at a single test statistic compared to the probability of whether that single test statistic would occur due to chance in the population, whenever we calculate a p-value, that calculation is based on the assumption that that is the only test we conducted. So basically, it's like flipping a weird extra dimensional coin. And there's a 95%, if we get basically the result of 5% or less, that means that there's a 95% chance or more that we were right. So we're basically saying that at p-value of 0.05, if that's what we find, the chance of that being an error, the chance that we would be wrong, is actually very small. It's 5% or less. And the chance that we're right is 95% or more. But the problem with the coin flip is that any coin flip is a unique flip. So every time we run a test, this is going to be true. But if you flip 5 coins in a row with a 50-50 odds, the chances of all 5 of them coming up heads or all 5 coming up tails is much less than 50-50. And that's the problem here if we run more than a single parametric test. Each additional test, though it is not greatly changing the probability because of this great disparity between 5% and 95%, it is slowly altering it. If I run 5 tests with a 5% chance or less of being wrong, and all of them come back as 5% chance or less of being wrong, of being correct, so I get 5 p-values of 0.05 or less. The actual chance of that occurring is smaller than 0.05. So we are actually running into an area where we are actually slightly warping the chances that we are in error. So we need to either make adjustments or move to more advanced statistics that are designed to test the data in multiple ways. So the effect does not change, but now each estimate of probability of error across all the tests tends to be underestimated. So just a brief review, this is the big chart of everything from 520, and just as a reminder, we covered a fair amount. We covered t-tests and z-tests for independent samples when we only have a single variable and it is continuous. and we have pre-known differences between groups that we compare to. We talked about if we have more than 3 variables, or 3 or more variables, and then the question is simply if they're categorical or continuous. And again, we talked about factorial ANOVA and multiple regression. We talked about if we only have 2 variables, if they're continuous versus categorical, and if whether they're between or within subjects, which statistical techniques we'd want to use. And I want you to continue kind of trying to think in these terms, and these are a little bit difficult to kind of conceptualize occasionally. But these are the questions you need to ask to get to the question or the answer of what statistic would I use. You always need to start with how many independent variables do I have, how many dependent variables do I have, and what kind of variables are they? Are they categorical or are they continuous? And if there was a difference in how I presented those categorical variables, are they between subjects or within subjects? Between, again, meaning different groups that never interacted versus within, same group interacting with multiple levels of that variable. And this is usually what's going to give us the information of what statistical test we should use, and that's going to continue to be true in this semester. So again, when we're talking about statistical tests, we want to think about the process. The first stage in any statistical test, no matter how simple or complex, is to compute the descriptive statistics and to check the assumptions, especially on continuous variables. We want to make sure that we don't have skewed data. We want to make sure it's not kurtotic. Again, either too high or too low, leptokurtic versus mesokurtic versus platykurtic. We also want to make sure that we're not having outliers. We want to check that data. Once we check the data to make sure that the assumptions are met in that data before we actually run our test, we want to choose the appropriate test and compute it. If we find there is significant value, that means that we want to evaluate the nature of the effect. Do we have statistical significance? Is the data reliable, and is the difference between our conditions or our variables strong enough that we can claim that it's not occurring due to chance? And if we are able to make that claim, we then want to evaluate the nature and size of the effect. What actually is going on? What does it mean in English? And how big is that difference? Because remember, the larger your sample, the larger your N, generally the more likely small effects will become significant. But those small effects may not be practical differences. Again, if I find a grade difference of 10% in a sample of 10, that's pretty meaningful. But if I find, and it might be significant, but I might also find that in a sample of 1,000, a grade difference of 2% is significant. Now, if both of those interventions cost the same, I would probably want the one with the larger difference. So we want to make sure that we're also attending to how big is the effect? How meaningful is the effect? Is the effect a good return on investment if we were to implement this in a real-world setting? A little bit more strategically or a little bit more stat-minded, the hypothesis stepping, the 4 steps again, is that we want to state our hypothesis. So remember that the statement of a hypothesis is an important part on the methodological side of statistical testing. We want to make sure that we're stating it, if we can, as an alternate hypothesis. In other words, that the IV has an effect on the DV, and that it's a directional hypothesis, that if the theory and past research gives us a reason to believe an effect will have a direction, we should state that. And then all experiments will have an assumed null hypothesis. We then state the criteria for rejecting the null hypothesis. Generally speaking, this has kind of been set for us, but it is something that we are doing, even if we just tactically are accepting the alpha of 0.05. Our third step is to then obtain a random sample. So that is the methodological step. That's designing the study. That's getting the sample. That's actually conducting the study and measuring our variables. And finally, step 4 is comparing the sample data to the null hypothesis and computing the inferential statistics. If we find the inferential statistics support our alternative hypothesis, we reject the null. The possibility of the result is less than the alpha. We found statistical significance. If we do not find a p of 0.05 or less, we have to fail to reject the null hypothesis. And the probability of a result is therefore greater than the alpha.